This video is a continuation of Lesson 4.1 on exponential functions. This particular video focuses on application problems, and we will be using our grapher and its home screen. Sometimes we'll use y equals, we might use table. We're going to use lots of aspects of our grapher. All right, the first application problems that we look at have to do with compound interest. This is a finance application, and everything we're going to look at is going to be a growth curve. That means that the base will be bigger than 1, and what we're looking at is future value formulas. We're going to put some money, P, into an account, and we're going to have a certain interest rate. Whatever it's given, we will change it to a decimal. And in most compounding problems, they say it might compound semi-annually. That's 2 times a year. Quarterly, 4 times a year. Monthly, 12. Daily, 365. So when it talks about the number of compounding periods per year, they use one of these words. All right, there is another kind of compounding where it says, let's let it compound, let's think about it compounding maybe annually, which is once a year, semi-annually, quarterly, monthly, daily, hourly, compounded every minute. If you compound it continuously, then the number E shows up in the formula and the formula changes. We're not going to go into a lot of details deriving these formulas. Both of them have to do with compound interest. One of them, when it is compounded so many times per year, and they will explain it in words, or continuously compounding as if n actually approached infinity. So let's take a look at number 15. Suppose you have $14,000. Well, that's the present value. That's P, 14,000. Which of the two rates would yield a larger amount in 4 years? And I'm so sorry, I left that out. Going back up here, the time is T, and it has to be in years. I completely left out the time. So time is 4 years, and they give us two choices. 6% compounded monthly. All right, so the interest rate is 6%. Change it to 0.06, and in that first scenario, if it says the word monthly, that's 12 times per year. In the second scenario, we still have $14,000. We still have time of 4 years. We still have an interest rate of 0.06, but it is continuous. So we have our two different formulas. Both of them, it just wants to know which one gives us a bigger amount. So let's find the amounts. A is equal to P times 1 plus R over N raised to the NT power. So that is 14,000. Open parentheses, 1 plus, this will be 0.06 divided by, because it said monthly, that will be a 12, close. Now, depending on your calculator, if you get a little box up here, then you can just type in it, N times T, 12 times 4. If yours says 14, suppose we do the same thing, 1 plus 0.06 divided by 12. If you get this symbol, you must use parentheses around the 12 times 4, or do it in your head and just put in a 48. My calculator uses this format. All right, so go to your calculator, and I'm going to completely clear off my screen, and I have on my home screen 14,000 open parentheses 1 plus 0.06 divided by 12 close parentheses. When I do the exponential housetop key, I can just type in 12 times 4. If yours does not stay up there in a little exponent spot, be sure and use parentheses around the 12 times 4. Enter. All right, so that is the future value if it's compounded monthly. Now, let's use the second formula, and I will bring this to my screen in just a minute. The second formula, when it is compounded continuously, is principal or present value times e to the RT. There, of course, is no n because it's compounding continuously. So this is 14,000 e, you don't have to put a times sign, but I guess you could, raised to the r, which is 0.06, times time, which is 4. My calculator, it will look like that. Some calculators, it will look like e, and there will be the house top. You must use parentheses 0.06 times 4. So mine will look like this. So I have 14,000. Second of the ln key is e to the x. 0.06 times the time is 4 years. Enter. All right. I should be able to grab this screen. And I have the first answer was the answer to this one. The second answer was the answer to this one. And I hope you can see that when you compound continuously, you earn a little bit more money. Because every time it compounds it, it adds the interest on and then starts the process over. And I completely messed this up. I am so sorry. I did not read carefully. I hope you were screaming at the video. This is 0.0593. So this is 0.0593. They reduce that just a little bit. 0.0593. I have to go back. So sorry. Let's go back to the calculator and do 14,000 second e to the 0.0593 times 4. Whoops. All right. This is the corrected one. This is wrong. So this was my first scenario at 6%. This is my second. The interest rate dropped just a little bit, but the frequency of the compounding went up, but not enough. So in this case, this is better. So I completely messed this up by not reading it carefully and having that wrong value. Once I put the correct value in, and I get rid of this one. Here are my numbers. And I can see that it was the first one. What you would understand from this, if I had not messed it up, is that actually the interest rate has more effect than letting n get, the number of compounding periods, get really, really large. All right, I apologize for misreading that. I was thinking that the interest rate stayed the same, but it did not. All right, let's look at number 16. Number 16, I'm going to use my calculator and I'm going to shortcut things just a little bit. In this one, I'll read the whole question. There is a video you can watch. Use the compound interest formula and the continuous compounding formula to solve the problem round to the nearest cent. Find the accumulated value. That is the future value. That's A. Find that if the investment is $15,000, so that's P, for 5 years, that's T, at an interest rate of 7%, never changes, so R is 0.07. The money is part A, compounded semi-annually, that means N is 2. Quarterly, N is 4. Monthly, N is 12. Continuously, we use PERT formula instead. Now you can do the formula for compound interest 3 times, or I'm going to show you something that might be considered a shortcut. You're looking for A. You can, for these 3, you can say define it as a function. Y is equal to, we know it is 15,000, open parentheses, 1 plus the interest rate is 0.07 over what keeps changing? The N. So I'll put an X there, raised to the NT power, but instead of N times 5, I'm going to put 5 times N, which is actually X. The thing that keeps changing, the independent variable, which is X, is the N, so I put an X there. What am I looking for? The Y. Now you don't have to do it that way. You can do it on a home screen 3 times using this formula, but let me show you how this can shortcut things. If you go to the Y equals, clear that out. Put in 15,000, open parentheses, 1 plus 0.07 divided by, it should be N, but I'm going to call it X, close, raised to, use parentheses if you need to, 5x power. Now I'm going to go to table. X is the number of compounding periods. When it's 2, I get this value. Now the only problem I have, and I do see this as a problem, it's, let me see. Oh, I can do that. You can go highlight it and you will see more. You'll see the entire number. This is $21,158.98. It's said to the nearest dollar. So I will put in 21,158.98. Now I can go back to this, come down, and I'm using my arrow keys to move things around, do it quarterly, put in a 4, enter. Go back up and sit on that number so you can see the cents. And the answer is $21,221 $2.67. You can't see the cents up here, but if you have it highlighted, you can. So now come down, back over here to X. Let's compound it monthly. Put in a 12, enter. Go over and up. This is $21,264.38. And what you can see from this is as the number of compounding periods increases, the future value increases. If you don't want to do this, you can, for instance, for example, let's do this one. On the home screen, you could have typed in 15,000 1 plus 0.07. For this one, n is 4, raised to the the nt power, so you probably would have it as 4 times 5. If you do that on the home screen, you will get this number. You can do each one of these on the home screen, or I showed you this shortcut of putting it in there. The value that's changing each time is n, so put variable x in the place of n. Now this one I need to do on the home screen. I'm just doing it once, so I'll do a second quit. There's my home screen. It is 15,000. Second of the ln key gives me e to the 0.07, it was 7%, times 5 years, close. Well, sorry, I never opened them. If you had opened parentheses, you would close them. And that gives me 21,286.01. Here it is again. And I can see, as long as everything else stayed the same, compounded. This one is compounded twice a year, 4 times a year, 12 times a year, and then continuously. And you can see the future value growing. It could all be done on the home screen, or you could have done those first 3 in the y equals. If you feel more comfortable doing it on the home screen, that's what you should do. All right, next problem. Let's see. I have my 2 compounding formulas. I need the accumulated value of an investment. That's my present value, or my principal is 20,000. My time is 5 years. My interest rate is 0.05. And semi-annually, n is 2. Quarterly, n is 4. Monthly, n is 12. And this is a whole different formula, P times e to the RT power. This time, just to be different, I'm going to go ahead and do it on the home screen. But if you want to try it, it would be y equals 20,000, open parentheses, 1 plus, the interest rate is 0.05 divided by n, which is x, raised to 5 years times x. And then you would do table. You would have x is 2, 4, and 12. And you would have to sit on these values so that you could see the cents. But I'm going to go ahead and do it on my home screen so we can have it all on there in case it's your choice to do it that way. So 20,000, open parentheses, 1 plus 0.05 divided by, the first time it's 2, close, raised to, the 2 times 5, NT. Remember, put parentheses around this if you need to. There's my first answer. My second one, got 20,000, open parentheses, 1 plus 0.05 divided by, this time 4, close, raised to the 4 times 5 power. Slightly more money. Now 20,000 times 1 plus 0.05 divided by, okay, when it's monthly, it's 12, close, raised to the 12 times 5, little bit more, and then the continuous compounding, so 20,000 second ln 0.05 times 5, interest rate times time, RT. And it is even more. So I'm going to grab this and hopefully, let's see, there it is. All right, first answer, that will stay at 69 cents. Second answer, 74 cents. Third answer, 17 cents. But the fourth answer, that will become 51 cents. So if you like the idea of doing it all on the home screen, you certainly can do it that way. That might be better if you're not feeling real comfortable with using the calculator for it. All right, let's look at number 18. All right, it says use a calculator with and we're going to use this key to solve the following. The exponential function f of x is equal to 545 times 1.026 to the x models the population of a country. F of x is in millions, x years after 1971. So you're going to have to be careful because x is the year after 1971. So if we were talking about 1972, x would be 1. Okay, so what I'm going to do is I'm going to put y equals 545 open parentheses 1.026 raised to the x power. I'm going to put it in my y equals. Five 45 open parentheses 1.026 close parentheses raised to the x power. All right, now I'll come back and look at that, and it says substitute 0 for x. It says without using the calculator, and find the country's population in 1971. When x is 0, you are 0 years after 1971. Now I'm going to do it with my table, but I want to show you. If x is 0, any base to the 0 power is 1, and 1 times 545 had better be 545. 545 million in 1971. But let's look. Let's go to second table, and I'm going to delete these old values, and I'm going to put in 0 like it told me to and enter. And even though it's very tiny, it's 545. That's what, and it is in millions. All right, next. Substitute 27 for X and use your calculator to find the country's population to the nearest million in the year 1998. Now, where did they get 27? 1998 minus 1971 is 27. X is 27 in the year 1998. So if they didn't tell me that X was 27, how would I get it? I would take the year and subtract 1971 from it. All right, so back to the calculator. I'm supposed to put in 27 for X, enter, and it said to round to the nearest million, so this will become 1090. 1090. What I did was table X equals 27, and I rounded. Next, find the country's population in this year. They're giving me the information to get another X. Anytime you're given an X, trying to find the Y, you're going to use table. So this one will be 2025 minus 1971, which is 54. X is 54 years since 1971. So I'll go back to my grapher, type in 54, enter. Rounding to the nearest million, it looks like it, let me double check. Rounding to the nearest million, I do not round up. And you could have easily made that mistake. Sit on the numbers to know for sure, especially if there's a 5. So 2179. This one was table X equals 54. The next one, the country's population in 2052. Let's see what that will be. I take 2052 and subtract 1971. I get 81. X is 81. So 81 years after 1971. 81, enter. Go sit on that so you know exactly what it is. It is 43584. So don't round up. 4358. There was a 4 and some other stuff, so don't round up. Now, this was table X equals 81. Now, you might not have realized it, but they went 27 years here since 1971, 27 years more, 27 years more. What is happening? Well, went from 1,090 to almost, this was almost 11,000 million, no, 1,100 million. I'm just going to leave off the million for a minute. This looked like about 1,100, and then about 2,200, and close to 44. It looks like it's doubling. And so I would choose A. I just compared these answers and it looks like each one of them is about twice as much as the one before. So you could have used home screen for this and done it 3 times. But when you have to repeatedly use a formula and you know what the unknown is that you're going to be plugging in, put it in the y equals and use an x for the unknown. The other little kink in this one is they use the phrasing X is the years after 1971. So you do the given year minus 1971, given year minus 1971, and so on. All right, let's look at 19. This one is not population. This instead will be radioactive decay, I believe. It says, in 1982, the 1982 explosion at a nuclear lab sent about 1,000 kilograms of radioactive element, they don't tell us what, into the atmosphere. The function f of x equals blah 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 describes the amount, f of x, in kilograms of the radioactive element remaining in the area x years after 1982. If even 100 kilograms of the radioactive element remains in the atmosphere, the area is considered unsafe for human habitation. Find f of 40 and determine if the area will be safe in the year 2022. Okay, couple of things. In the year 2022, if I subtract 1982, I get 40, and that is my value for x. But they told me that. They want me to find f of 40. Since I just have one problem to do, not multiple problems, I can do it on the home screen pretty easily. I could, if I wanted to, use table. It wouldn't matter. So I have f of 40 is 1,000 times 0.5 raised to the x, now x is 40 over 30. Okay. If I did it in the y equals, that would be an x, and then I would use table and put 40 in the place of x. No real reason to do that when I only have one problem. So, oops. All right, clearing that out. F of 40 is, I have 1,000, open parentheses, 0.5, close, raised to the x, which is 40, divided by 30. And I get, wants it to the nearest tenth, 396.9. 396.9. Now, let me take a minute to explain a little bit about what's going on. This formula up here at the top is called the half-life formula. As time passes, half of a radioactive element will change its molecular structure and become non-radioactive. Half of it will. The other half will remain radioactive. The curve, if you were to look at this, it would look like this, and it would be declining or decaying. This is when it starts, when you have the full amount, in this case 1,000 kilograms. After 40 years, we will have 396.9 kilograms. This is rounded to the nearest tenth, the 396.9 kilograms. Will the area be safe for human habitation in this year? Well, the answer is no, because the radioactive element remaining in the area is greater than 100. And they said that it's unsafe if there's even 100. And there's there's almost 4 times as much. So this is no. This is an exponential function because the because the base is a value between 0 and 1, it's a decay curve. All right, let's look at this one. These are all different applications. This one says the function f of x equal to 90 times e to the negative 0.4x plus 10 describes the percent of information, f of x, that a particular person remembers x weeks after learning the information. We have several things to do. They're talking about, they're changing up the number of weeks, which is x. So I'm going to go to the y equals and put in 90 times e to the negative 0.4x, and then I'll be going to table. For the first one, it says at the moment first learned, x will be 0. That's how many weeks it's been after learning it. Part B, it's 1 week after learning it, 8 weeks after learning it, 1 year, which is 52 weeks after learning it. And we'll see what percent is left. All right, go into my calculator, go to my y equals, clear out what's in there, and let's see, it is 90 second of the ln, and this is negative 0.4 x. Use parentheses if yours is different. Now, if you're using one like mine, you've got to get out of that and then plus 10, because we have a plus 10 that is not in the exponent. Go to second table. All right, I'm going to delete these. All right, I'm going to put in 0. That is 0 weeks. And I will remember 100%. Then, after 1 week, I will remember, and let's see, it says to round to 1 decimal place, 70.3%. Then, I want to look at 8 weeks. I only remember 13.7%. And then a year, 52, I only remember about 10%. My memory of this information is declining. So my answers are 100, 70.3, 13.7, and 10. This is a decay curve. The negative exponent puts it 1 over e, makes it a fraction, and that's what's going on. That's why it's decaying. All right. This is just kind of an interesting question. It's our last one. It says, in 1857, a person sold a house to a lady for $26. If the lady had put the $26 into the bank, now that is at that time the present value, paying 6%, so the R is 0.06, how much would the investment have been worth in the year 2012? Okay, let's see, 2012 minus 1857, it's going to be 5. I will have borrowed, that is 155 years is my t value. If the interest were compounded in the following ways, so I'll just write up here that t is 155. All right, compounded monthly, n is 12, the investment would be worth blank. So let's see. A is equal to P times 1 plus R over N raised to the NT power. So this will be $26, 1 plus the interest rate is 0.06 divided by, if it's monthly, that's 12 times a year, to the 12 times, now what's going to make this be drastic is 155 years. So let's see. Do a second quit. 26, open parentheses, 1 plus 0.06, that's my 6%, divided by 12, close, raised to the 12 times 155. Okay, I think I lost it. $277,874 rounded to the nearest dollar. The other choice is, what if it's continuously compounded? That's P-E to the R-T. So it is 26 E raised to the 0.06 times 155. So it is 26 second of the ln gives me E, 0.06 times 155. I'm sorry, that's so tiny. Significantly more because of the amount of years that this went on. It is 284,388. So let me go to the calculator, grab this, whoops, thought I could just move it up. I can. So those are my two answers. This is compounded monthly, and this one is compounded continuously. So that was just one more example. In each one of these, we have either had a growth curve and we're watching something increase in value, but once in a while we have a decay curve and we're looking at something decreasing in value. The functions are given. It's a matter of, can you either use your home screen, or if you want to, the y equals, to find these values.